Hi, everybody. Today we're going to talk a little bit about our satellite project that we built in collaboration with Adelaide Uni and Uni SA. So kicking off, it's a bit difficult to, the other way. Okay, so we built a CubeSat. So what is a CubeSat? Well, a CubeSatellite is a small satellite made up of units of 10 by 10 centimeter cubes. So the one on the screen that you can see here is our satellite, and it's a 2-unit satellite, which means it's 10 centimeters by 10 centimeters by 20 centimeters, essentially. Now, a small satellite or a CubeSat has all the subsystems that a normal satellite has. They're just very small. So we have an onboard computer, which essentially controls everything about the mission, when things turn on, when things turn off, when we're going to talk to it, when it should go into different modes, such as when it should go to fine pointing mode or when it should be detumbling or whatever mode you want. It also has a power system, so you can see the solar panels on all of the faces. So that they obviously generate the power. There's a battery on board that stores the power, so then your power system manages the charging of the battery to ensure that you don't overcharge it, although that's relatively unlikely to happen. It's more likely the other end of the scale that you don't discharge the satellite completely so that it can't recover. So basically, the power system manages all the power aspects of the satellite. Then you have a pointing system or an attitude control system. Patrick will talk a lot more about that in a little while, but essentially that points the satellite in the direction that it needs to be pointing to conduct its experiment. And then you have a communication system. So that's the system to enable you to get the data off the satellite or to send commands back up to the satellite to tell it what to do. So why would you go for this miniaturized platform instead of a large satellite? And the bottom line is cost. So launching a satellite like this costs about $150,000 as opposed to launching, when the space shuttle, for example, puts a satellite in orbit, it's about $300 million. So it's significantly cheaper, and there are a whole lot of things you can do with this type of platform. I mean, there are a number of things that it's not particularly well suited for, but there are a lot of scientific missions that you can do. The last thing I forgot to discuss about the satellite is the reason it's there, and that's the payload. So the little cylinder that looks like a tuna can on the top, that's the payload, and I'll discuss that in a little while. Okay, so what's inside it? So inside, as you can see in the image, there's a lot of electronics and a lot of wires. So the structure around it, which is basically what holds the spacecraft together, is just a machined aluminium structure, and it's just 6061 aluminium, which is relatively common. You can see a shiny silvery paper covering the one square on the screen there, and that's a thermal blanket. So the temperature variation on the outside of the spacecraft goes from about 150 or 160 degrees down to about -50. So consumer-grade electronics, in fact, even industrial-grade electronics can't handle those sorts of temperature variations. So you've got to moderate the temperature inside the spacecraft. So on the bottom quarter, or the bottom half of the spacecraft, there's a thermal blanket all the way around and on the back. And you'll notice that this side doesn't have a thermal blanket on it, and that's because that's facing the Earth. And the Earth's very forgiving from a temperature point of view. So when it's very cold outside, the Earth keeps you warm, and when it's very hot outside, the Earth keeps you cool. So you always you can radiate to or from the Earth as required. Then some of the boards that you can see, the bottom two boards here are battery and, the onboard computer. The ones at the top there are the battery and the power system. Down here we have an attitude control system. This here is a reaction wheel. So in fact, it's a momentum wheel and a reaction wheel. So it operates on the same principle as a bicycle wheel. So you're going forward in your spacecraft, and the wheel is spinning in this direction, so it resists motion in the roll direction or in the yaw direction, but changing the speed of the wheel can make you pitch the satellite up and down. And this is the GPS receiver. And the square cut out of that you can see in the top of that image is the hole for the GPS antenna. And then the lens that you can see at the top there is a sun sensor. Why don't you scroll it for me? Go. Thanks. So what does it do? So as I mentioned, the whole reason you go up there is for a particular experiment, and this is our payload, and it's called an INMS, or ion and neutral mass spectrometer. So this is an instrument that measures oxygen, and nitrous oxide and nitrogen densities in the upper atmosphere and the ions. So the area of interest is called the thermosphere. So this is a very poorly explored part of the atmosphere, and the reason for this is that satellites don't last very long in that area because there's still a little bit of atmospheric drag. So depending on the amount of solar activity, that thermosphere can expand up to above 400 kilometers when there's a lot of activity, and then it can shrink right down to sort of 250 kilometers when there's only a small amount of activity. So basically this tracking of where all the particles are and what the densities are is the whole purpose of this mission. So just you can see in the context of aircraft sort of operating at the top of the troposphere, then you have the stratosphere, the mesosphere, and then the thermosphere, and there's actually one on the top called the exosphere, which we don't really talk about. Next one. All right, how do we talk to the satellite? So we have a ground station in Mawson Lakes, and it operates in the UHF band. So as you can see, you have just a standard Yagi antenna, which is like a TV antenna. And it's a tracking antenna, so as the spacecraft is viewed on the horizon, it beacons to us, and then we lock onto it, and then it sort of tracks the spacecraft as it's going over, and then we can talk to and from it. And there's just a ground station, which is essentially just a software-defined radio and a computer that's attached to it. And we can do things like type up commands. So we have a diagnostic system where we can work out what the spacecraft is doing and what it thinks its state is and what it thinks various things that it's measuring are. And we can basically interrogate anything like that, just like you're typing into a computer. It goes over the comms link, gets executed on a computer, and comes down. And it's got a fair bit of latency. It's probably, it's sort of a 5-second turnaround, so it's quite painful typing commands up and down to it. I think that's probably next one. I think there's one more. And then the last thing to talk about was a bit of testing. So when you design what needs to be made, you have your set of requirements. You have to build what you need to build. Then you have to test that everything works properly. So what we've got is environmental testing to make sure it'll survive launch, and those are the two on the left. That's the shaker test, and that's a thermal vacuum test. And then on the right, just sort of showing how the spacecraft will operate. So that's just a sun simulator to check the solar panels work, and then a magnetorquer calibration experiment. Go. I hand over to Patrick now to talk about the attitude control system.
All right. Thank you, Matt. Yep, I'm Patrick Philbey, and I'm going to be talking about the work I did contributing to working on the CubeSat project as part of my final year project at Adelaide Uni. So Matt's given us an overview of the satellite in general, and it's clear that there are a lot of subsystems, and I've got it. And our work this year has really, so when I say our, Jade was also a part of my final year project. She couldn't make it today because she has an exam tomorrow, but our focus this year has been on the satellite's attitude control system. So for our payloads to deliver really good results while it's in orbit, it needs to kind of have a stable attitude. It needs to be constantly pointing in the same direction. In the thermosphere, as Matt mentioned, there is still a very small amount of atmosphere, just a few particles almost, and these eventually kind of disturb the satellite, and it starts to spin up after a little while. So we want to be able to control that. And so that's where the attitude control system comes in. So the attitude control system can be broken down into two parts. The first part is the attitude determination. So that's taking input from its sensors. It's got a sun sensor. It's got something called a nadir sensor, which is where it's always looking for the horizon of the Earth. And it's got a magnetometer for measuring the magnetic field in orbit. And it's got a gyroscopic sensor for measuring how fast it's rotating at any time. So it takes all the data from those sensors, and it basically puts it all through an algorithm called a Kalman filter, and that gives you a really reliable value for its current attitude, taking all those inputs. But then once you've got that attitude data, you need to use it somehow, and then you've got the attitude control part, which is taking all those inputs and calculating how do I use my actuators to actually maintain the attitude. So Matt mentioned the reaction wheel, but we've also got 3 magnetorquers as well. Magnetorquers are essentially just coils of copper wire, and when you put an electric current through them, and you're in a magnetic field, you get a bit of torque on the satellite. So we can control that torque, and we can calculate what torque should we use to actually to turn against the Earth's magnetic field. So our project was about how we can improve the control methods on there, and actually how can we test this attitude control system down here on Earth. Yep.
I reckon just go to the cage. You're probably running out of time. Probably go to the cage.
Yeah. Sorry. So I'll just quickly skip a. Yep. So onto testing the attitude control system. It's not so easy to test a satellite here on Earth, because in space it's a vacuum. There's no friction. Once something starts spinning up, it doesn't really slow down. So we use something called a Helmholtz cage, which has a hemispherical air bearing. We put a mock-up satellite, a mock-up of CubeSat, onto this air bearing, and it could spin freely on 3 axes. And then we also use, and the Helmholtz cage itself is just a set of 3 orthogonal magnetic coils, 3 orthogonal coils, which lets you change the magnetic field actually inside the cage. Because in orbit, the satellite's going around the Earth very fast. It means the magnetic field is also changing very fast as it moves around, and that lets you emulate. That actually lets you emulate the low magnetic fields, such as in a place called the South Atlantic anomaly over the South Atlantic, where the magnetic field is very weak and in a weird, strange direction. So it lets us. This method, it lets us test the satellite software in a real-world environment where it would usually be quite difficult to do that. So I think that's it for our presentation. That's it for our presentation. I hope you've enjoyed it. So, yeah.